And now we have an online talk by Wlodek Kluzniak. You can hear
hear
us?
me
Yes,
well?
we can hear you very well.
Right, let me share then the screen. Okay. Can you see the transparency?
Yes, yes, we can.
All right, thank you.
Okay, perfect. So you have 15 minutes, and I'll try to interrupt you to let you know when you have 5 minutes left before the
All
end.
right,
Okay, thank you.
thank you so much. First of all, I'd like to apologize for not being there in person. I had every intention of doing that. And I'd like to thank Natalie for suggesting that I give my presentation online when my plans did not work out. So let me start by explaining the title. Right, and this is a bit of a tribute to Jean-Pierre Lasata, who passed away recently. So some 20 years ago, we published a paper stating that there is really no electromagnetic proof of the existence of a black hole horizon. And as Jean-Pierre insisted, or rather stressed, it is not a question of not having that proof yet, but it's a question of principle. In principle, no electromagnetic observations that we can think of can demonstrate that a black hole horizon exists. So that's why we need LIGO and Virgo for the binary black hole coalescences to teach us that black holes exist indeed. But when it comes to supermassive so-called black holes in the centers of other galaxies and our own, we do not understand the origin of those objects as well as we do of the stellar mass black holes. And I will not go into the formation scenarios, but I will say that the situation is even more dire for Sagittarius A star and the supermassive compact objects in the centers of galaxies. For example, LIGO and Virgo is helpless because the frequency of anything that goes on there would be completely off. So to summarize the talk, painting with a very broad brush, observations by eLISA, or is it eLISA rather, if there is an inspiraling compact object or even a star around Sagittarius A star or another supermassive compact object nearby, you're going to see a continuous wave for a very long time. And then, if you're lucky in a statistical sense, I say lucky because for Sagittarius A star, because of its low mass, we know for certain that on average, the Sagittarius A star does not coalesce with stellar size objects very frequently. So you have to be very lucky for that. But in principle, what you see is a continuous signal that comes to an abrupt end, and there is no electromagnetic signal following that, or no gravitational signal either. And that is the smoking gun of a horizon. Now, you may be surprised that I'm considering Sagittarius A star. We have all seen the iconic image of the Event Horizon Telescope. And the Event Horizon Telescope collaboration has done a very careful job of showing that the image that they were able to observe through technological breakthroughs is completely consistent with the silhouette of a Kerr black hole of the mass of the compact object in our Sagittarius A star center of galaxy. Okay, so there is at present no compelling need to consider any other objects, but let us open up our imagination and say, what if the image that you see is actually what it is? When I look at the image, what I see is a torus, a donut. So let us assume that it is a donut. Okay, as you can see on the right-hand panel, a vertical cross-section through that torus. Okay, if the observer is looking down the hole, you would see a dark hole surrounded by a bright area. And such tori, actually, such donuts, can exist around naked singularities. And the shape that you see on the right is actually computed. It's not an artist's impression. It is the computed shape of a figure of equilibrium, fluid orbiting a naked singularity. So now let me tell you what a naked singularity is, in case you think I have segued to the next session and I'm talking about exotic scenarios. No, I'm not. This is not an exotic scenario. This is a standard solution of in Einstein's theory of general relativity that is as old as the Schwarzschild solution, Reisner 1916, Nordstrom 1918. Okay, and certainly it's much older and much simpler than the Kerr black hole solution that we all love and use. And what is a naked singularity? Well, we use naked singularities all the time in physics, and in chemistry to think of an electron. Okay, if you don't go to quantum mechanics, classically, it's a point charge and a point mass at the same time. And there's something called the classical radius, which is the radius that a point charge. Sorry, this is the radius. So this is if the mass of the electron as observed is the result simply of the electromagnetic interaction that is within the radius R0. This is the classical electron radius, right? Okay, for an electron, obviously, the mass is so small that in fact it is a quantum object, so we cannot see the inside very close to the point naked singularity charge. Okay, and the electron is shrouded by quantum mechanical effects. The quantum wavelength is larger than this classical radius of the electron. But if the mass were larger, for example, if it were a microscopic mass, the quantum effects would be negligible in the sense that the quantum wavelength would be much smaller than this classical radius. And in GR, in general relativity, as shown by Reisner and Nordstrom, okay, there is a solution for a point charge and a point mass, and it took some, I don't know, nearly 100 years to show that in fact that solution also has a characteristic radius, which by accident perhaps numerically is equal to the classical radius that we know from the electron. So if you have a mass m and a charge q in gravitational unit, there is a magic radius, a sphere, at which gravity is no longer attractive towards the naked singularity. And in fact, within that sphere, gravity is repulsive. So here on the top panels, I show the effective potential of a charged mass according to the Reisner-Nordstrom solution. I'm not sure if you can see my arrow, my cursor, but anyway, as you can see, the effective potential has a minimum, and closer to the naked singularity in the left part of the top panels, there is a very strongly repulsive core. Now we can imagine then a fluid body in equilibrium rotating the naked singularity, and depending on the angular momentum, the cross-section of this topological torus will be more or less distorted. As the fluid body gets closer and closer to the naked singularity, as you can see in the figure, that it gets more and more distorted. You can actually do a simulation and compute the standard accretion scenario for naked singularity, just as you would in a black hole. So in the left panel, you see a large torus, so a mock-up of the accretion structure, if you will. A large torus, this is the standard thing that's done in GR in accretion simulations onto Kerr black holes, except that here we have a black hole in the Reisner-Nordstrom metric. So if you see the black contour, within which the fluid resides on the right, in the inset especially. Okay, this contour is a self-intersecting equipotential surface with a cusp. So you don't need to do any work. You just fill the outer torus with fluid up to this cusp, and then it will just flow over. It's like Rorschach overflow, except that here there's toroidal symmetry. You're seeing a vertical cross-section through it. Okay, and as you can see on the left, essentially all the fluid that spills over through the cusp gets absorbed by the black hole. On the right, you see the same situation. The charge has been increased just a little bit so that from a black hole solution you go to a naked singularity solution. And now you see that the fluid does not get to the center. It forms this toroidal-like structure very close in to the black hole. All right, so
Wlodek, you have 5 minutes left.
yes, thank you. Then I'll skip this and I will move to this point. Okay, so here I am showing again the effective potential in the right panel for different angular momenta of test particles. Okay, obviously the test particle will be in a circular orbit for any given angular momentum at the bottom of these potential wells. And on the left you see the test particle angular frequency as a function of the radial distance from the naked singularity for different charges of the naked singularity. And you can see that as you go from the right to the left, you can see that essentially we have the familiar Keplerian curve from GR, from Newtonian physics, except that there is a maximum and then a drop in the angular velocity. And eventually the test particle may rest at the zero gravity radius. So the point is, of course, that if you have an orbiting body around Sagittarius A star, and eLISA will track the frequency of that body. Okay, you can, even far away from the naked singularity, you can see the departure from the say Schwarzschild-Kerr dependence of angular momentum as a function of the radius, but a very dramatic thing. So now here I'm not talking about the horizon, I'm giving you an alternative thing that Lisa may see. A very dramatic thing may occur if the body approaches the naked singularity. Its angular frequency, so the continuous wave seen by Lisa, will start dropping in frequency. All right, so let me skip this. Okay, it is possible also to do a simulation of a thin accretion disk with which we are more familiar. And on the right panel, what you see is the circles show the predicted test particle angular frequencies, orbital frequency, and the continuous lines show those in the disk. So it's all right. So this is standard accretion disk physics for thin disk. All right. So the point is this: that EM observations of Sagittarius A star, in spite of great technological advancements, are always open to interpretation. So you see something, okay, it may be consistent with what you expect, but there may be other pictures that it is also consistent with. So if you really want to be sure what Sagittarius or the other supermassive compact objects in other galaxies are, you really need to go to gravitational wave detectors. Thank you.
Thank you very much. Are there any questions in the room or online? So I guess I'll start with a question. Oh, go ahead. Sorry, I didn't see.
Can you hear me?
Yes, I can hear you.
Thank you for the talk. I was wondering, I So I know that, for example, by looking at the light rings around the supermassive black hole, you can connect this information to the remnant, to the
So
black
sorry,
hole
could you repeat
parameters.
that? Okay, let me plug in my earphone. Maybe this will be better. Yes.
Yes, sorry, we'll try to speak louder. Can you hear me now?
Okay.
Is it better now?
Yes.
Ah, perfect. I I was wondering, I know that by looking at the light rings around a supermassive black hole, you can gain information on the black hole, especially if you manage to resolve multiple light rings. So my question is, does this picture change when you consider naked singularity and you remove the horizon? Like, will the light rings will change or not?
Yes, of course. Okay, the structure of the light rings is a little different in some naked singularities. For example, in the Reisner-Nordstrom, in addition to these unstable photon orbits, which create these light rings that I think you're referring to, there is a stable photon orbit also. So yes, the structure will be different. And if you assume that what EHT sees is in fact the shadow of a black hole, then you can constrain the metric and perhaps eliminate some of the naked singularity solutions. But there's an assumption going behind it that you have to identify what you see with a certain model.
Thank you.
I'm not sure if I answered your question, but
Hi, Wlodek. Thank you for this really nice talk and also for mentioning Jean-Pierre Lassota. That was nice. I just wanted a clarification. So the object that is orbiting the black hole, it needs to be a compact object, am I right? Yes? Or could it be any other kind of object?
right. The problem with a non-compact object is that we need to worry about tidal disruption. So if it gets too close to the source, be it a black hole or a naked singularity, it may be disrupted. But other than that, no, it need not be like a Newton's star. Even it could be a planet, okay, and at a certain distance, it could be an ordinary star that will be tracked. Yes, but you need to get close to have a precise measurement of the difference between the Kerr solution and some other solution that you may want to consider.
Thanks.
Thank you. Any other question? Anyone? No? Okay, so I suggest that we thank Wlodek again.
Thank you
for
so
your
much.
talk.